the last lecture of our annual meeting. It's my great pleasure to introduce Professor Shenardi from North Norfolk originally from Rutgers University. And in the lecture on his basic necessary.
Thank you very much for introducing me. I am grateful to the organizing committee to invite me, and especially I am grateful to the audience who willing to suffer in 1 hour. I promise you that my lecture will not last more than 1 hour, and just reduce the damage. Also I have to admit that I am very nervous giving lectures, and usually it ends up with not so good lecture, but at least I give the respect to the audience and see. I am prepared to rest, so that is how I really want to make a good impression. Okay, so let's start with the lecture. The type is laziness paid both. This is a question mark because it is not necessary. We all know that it is the truth. That laziness is paid both. But of course, as I told already yesterday to some of my colleagues who asked why this in the title, and I have to admit that there is no other reason except that when I was growing up there, I didn't give such a title, but nowadays one of the most important things is this, what is this PR stuff, and then of course this is just part of the business, but I am not sure that the right one is not the most important aspect of everything, but let's assume that it is just part of the thing. But actually the real type is I have to also practice, you see, the real type is that solving method. I always apologize in my whole life that half of the time I apologize, and the half of the time I explain why I shouldn't have done this. That I am right-handed, but you see, I never, once or twice I use this PowerPoint, and I always use my right hand because I am writing with my right hand. So what you see on there it is written with right hand, but first time in my life now use the PowerPoint with using my left hand. So if something will go on wrong, that my friend will help me to correct the program. Okay, so anyway, I am associated with the Institute at Rutgers University, but basically I am Hungarian, and just to make a living I went to the US. The reason, but I am sure that I am not alone with this. Okay, now let's start with, and I am going to talk about things actually which I myself understand. Actually, this is not an easy task for me, but and then I will start with the notation, with the very basic notations. But if you say that you know everything, then please stop me, and then I will go further. So I will just give a whole history, and then at the very end, why we have the absorbing method, which is a new method, maybe it's 3 or 4 years old methods, but I need an introduction for that. So notation very well known. This is standard. We have a graph where vertex set is denoted by VG and the asset is denoted by EG. And then the absolute value VG means that the number of elements in VG is equal to, and this is the standard notation. And X is V. If we take a vertex in your graph, then the neighborhood, which is denoted by an X, is nothing else, just the set of Y, so that XY will form an edge. And then the X is just the degree of the point X, so absolute value of the not absolute value, but the size of its neighborhood, and delta G is the minimum of all of these degrees. And then the whole extremal graph theory started with this very simple observation, but it was like, I don't know, 70 years ago, maybe more, and that is just an exercise, I would say even a high school exercise in a town, in a country where actually the education is not at the top level, but it's so easy to do that almost everybody immediately can solve it. So it's well known by now, if the minimum degree is at least 10 over 2, then we have a one factor. I always assume that by like 2 divides, and I don't want to deal with the integer part and so on. So therefore, if there is a divisibility requirement, then I always assume that this is not a problem. Like here, of course, if n is an odd, then there is no one factor. Which is a one factor? The one factor is the x is the set of empty edges, so that you have all the vertices included. But of course, if n is odd, then one point has to be left out. But we don't care with this, so we assume always that n is fine. If it has to be divided by 3, then n is 3 times k. Okay, so that is a one factor. And this is, one would meditate whether this is tight. Maybe then you don't need this requirement, then all the minimum degrees are over 2. But no, this is an easy counter example. Look at this, then we have a graph, so that we divide the vertex that is A1 and A2, and the A1 size is n minus 1 over 2, and A2 size is n plus 1 over 2. So, and then inside you have a complete graph, which means that every 2 points inside is connected. So it's a complete graph. So in both A1 and A2 are complete graphs. And obviously, you don't have a one factor in it because, no, sorry, maybe I just will tell you that not this is not the best example. Maybe the easier, then we have all the crossing edges. Okay, so just forget it. This is empty, and we have all the crossing edges. This is also a good example, but better one if it is just crossing edges. We have, it's not on the picture, but you understand what I'm saying. That one endpoint is in A1, other endpoint is in A2. Yes, and then inside A1, this is empty, and inside A2, it is empty. I changed my mind, sorry, because this shows most what we are talking about. And why there is no one factor? Because one factor has to contain 1 point from A1 and 1 point from A2. But then how many points we have in A1? Only that many, yes? So that n minus 1 over 2 multiplied by 2 is only n minus 1. So we don't cover all the vertices. You see, so that's an easy example, not this one, but the modified one. But if this one also, because if it is in the correct, then 1 point will be left out. So this is tight, and that is an exercise, really, it's not another. So, actually what really started, what really started the extremal graph theory, which is by now it's a huge subject, but in graph theory, and the Dirac's result was the first one which really told something surprising. That what Dirac's result actually says to us, then if the minimum degree is n over 2, notice that this is exactly the same n over 2 as we had before, yes? So n over, if the minimum degree was n over 2, then we had a one factor, and it was time. That was an important point. But now, if the minimum degree is n over 2, if I ask you, is it enough to have a Hamiltonian cycle, then the Hamiltonian cycle is nothing else than we order the vertices V1, V2, V3, V4, V5, and the end, so that every 2 consecutive vertices is connected. Then Dirac's result says that if the minimum degree is at least n over 2, then we have a Hamiltonian cycle. But I will just before, the program is the following thing, that is what I wrote and that is what I asked from a professional to put in with the computer. And then I overlooked that the expert didn't put here a Hamiltonian cycle. So this is my handwriting and this is what was done with computer. So therefore sometimes maybe I overlooked that some figure is missing. But now I write here just so that we do agree that we know V1, V2 and so on, Vn. And so that is a Hamiltonian cycle, contains all the vertices, V1, V2 and so on, Vn, and every consecutive vertex is connected. Now you understand that this is much richer structure than just a one factor, because if I erase this edge, then you see that if of course 2 divides n, then we will have a one factor. Yes? So once I have a Hamiltonian cycle, then of course Hamiltonian cycle contains the one factor, assuming that the number of vertices is divided by 2, because you just erase every second vertex and then you can see you got the one factor. So that is a much stronger, would have been a much stronger picture there. Okay. Now let's go one step further and then modify the condition. And now the minimum degree is 2/3 times n. And that was Erdős's question, that you see 2/3 actually is bigger than 1/2, so it is 1/2 times n. So what can we say? And then Erdős asked and Hajnal and Konrad solved it, that if the minimum degree is 2/3 times n, then our graph contains a triangle covering. Of course, also a triangle covering is a more complex notion than a Hamiltonian cycle, because if everything is and so it's much harder to prove that if the minimum degree is n over 2, then it contains a Hamiltonian cycle. This theorem started a development of that kind of investigation, and then we call this whole thing a triangle cover. You cannot, you can see that every vertex is in one of the triangles, and these triangles cover all the graphs. So every vertex you can see, and what is more important, of course, than any two triangles are vertex.